All right. So Earth has now found a new balance. Now, that being said, there are still things that throw that Earth off of balance. The shape of Earth's orbit changes over time. The tilt of Earth's axis changes over time. The placement of continents changes over time. And each one of these things actually does have implications on Earth's climate. Then there's also prehistoric catastrophes, things like asteroid impacts, major volcanic eruptions, gamma ray bursts, major dying off events, new feedback loops that are kicked in, mass extinctions. Well, that takes us into part 3 of our little journey into the reconstructed climate. So here's what happened next. What happened next, as Earth began to sort of reach this new happy medium, we began to see a new seesawing, not nearly as extreme as the old seesawing that we saw, but due to other forces such as continental drift, volcanic eruptions, and so on, we've seen these major glacial periods. We love to call these ice ages. Ice ages, not to be confused with the movie with Manny the Matador, and my little favorite, Scrat and his little acorn, that poor little guy. Well, we have had 3 major glacial periods, 3 major ice ages. 700 million years ago, 300 million years ago, and 2.5 million years ago. This most recent ice age is what is referred to as the Pleistocene epoch. And we are still technically in this. We are still technically in an ice age. So, Terrence, how do we know that the current rate of warming isn't just us getting out of that ice age? Well, I'm glad you asked. We'll actually talk about that in a few minutes. But let's actually talk a little bit about what else happened during this time. So we've had these major glacial periods, and then we had some nice warm periods. The most recent really warm period was the age of the dinosaurs. And so the dinosaurs were doing fine. They were thriving. You had Littlefoot and Sarah and Ducky and all their little friends in the land before time. I was watching those when I was a kid, and I think, what are they on now? Like the 35th movie, The Land Before Time and the Great Pandemic. Hopefully they're not doing that. Well, unfortunately, poor Littlefoot and his friends' lives eventually came to an end. 66 million years ago, an asteroid called the Chicxulub asteroid, an asteroid that was about 6 miles in width, so a big 6-mile wide asteroid, began hurling towards planet Earth. It made impact in the Yucatan Peninsula. And I know what you're thinking. Okay, so 6-mile wide asteroid, that's going to destroy a city, maybe a small country. No. This kind of an asteroid coming to the Earth at the speed that these things come at will cause worldwide destruction. Will cause worldwide destruction. And only smaller animals that can find shelter and don't need a lot of food are able to survive that. Well, dinosaurs are big. Dinosaurs need a lot of food and they need big shelter. Well, guess what? Because of a major asteroid impact like this, they don't get that. So unfortunately, very, very quickly after the impact of the Chicxulub asteroid, the dinosaurs went away. Meanwhile, the little mammals, these tiny little things that could burrow in holes and didn't really need to eat a lot, survived. That is how we eventually came to be. Those little prehistoric mammals eventually brought us to where we are today, at least based on the scientific evidence we have. The reason why this happened, though, was because of a phenomenon called impact winter. So basically what happens is when a giant asteroid hits the Earth, it kicks up a lot of crap, a lot of dust, a lot of debris, all kinds of gases and clouds. And I mean, I'm talking on a massive scale. And this stuff spreads all around the world, and it can actually stay up in the atmosphere for years and even decades. It can shade out the sun, leading to a very, very, very cold period, oftentimes referred to as nuclear winter because we think about, what happens if we blow the hell out of each other up, or if we blow each other up. Um, but also referred to in this case as impact winter. And unfortunately, Littlefoot and his little friends didn't make it. So that is the very last installment of The Land Before Time. I know, sorry, Littlefoot. So catastrophic asteroid impacts have caused very sudden, very drastic changes in climate. Something else happens as well. Supervolcanic eruptions. So there are thousands of volcanoes that litter the entire surface of the Earth. Most of them are either really tiny or are capable of very minor eruptions. However, there's a handful around the world that are capable of what are called cataclysmic eruptions. These are what are referred to as supervolcanic eruptions. A supervolcanic eruption is an eruption that ejects at least 1,000 cubic kilometers. That is a cube 1,000 kilometers wide, 1,000 kilometers deep, and 1,000 kilometers tall. That is a huge, huge thing. That is an exponentially huge thing. That is really big of ash. And when you have a supervolcanic eruption, it is hurling all of that ash high up into the atmosphere, into the upper layers of the atmosphere, which the weather up there is really boring. It's more boring than a Terrence Mullins lecture. Way more boring than a Terrence Mullins lecture. And so all of that stuff, when it ends up there, it stays put for a while. And it eventually fans itself around the world. This leads to what's called volcanic winter. Volcanic winter. We here in the United States know of the world famous Yellowstone volcano. It's this gigantic, roughly 50-mile wide caldera. Basically, like it's a giant dip in the earth. And inside this dip, there are all these hot springs, there are all these prismatic pools, there are geysers, there are all kinds of crazy things that are being fueled by the heat of the big patch of magma below, the big chamber of magma below. Well, what happens is over time, magma chamber continues to fill up and fill up and fill up. And approximately every 600,000 to 800,000 years, that magma chamber becomes too full and then boom, it erupts. Well, guess what? The last major Yellowstone eruption happened 640,000 years ago. So these eruptions are happening roughly every 600,000 to 800,000 years. In terms of geologic time, we're due. Now, does that mean that the volcano is going to erupt before I can even hit send on this video? No. By saying that we're due, we're talking tens of thousands of years from now. And even if there were to be a Yellowstone eruption, we would actually know about it. We would actually know about it well in advance. Still, it would be a pretty scary situation. It would actually be really frightening. I mean, just this image right here shows that the entire United States, this was actually from the last Yellowstone eruption, the entire United States would be covered in at least 1 millimeter of ash. All but the southernmost portions of the United States, extreme southern Texas and extreme southern Florida, would be covered in ash. And even just a little bit of ash is enough to ground or to shut down an airport. In some places like Montana, Idaho, and Utah, up here, Montana, Idaho, Utah, Wyoming, this whole region up here, these states would practically be wiped off the map like that. But that's not the only time that we've ever had major supervolcanic eruptions. The last major supervolcanic eruption happened about 75,000 years ago at Lake Toba in Indonesia. What is so scary about this eruption is that it messed up Earth's climate so bad, it is believed that it actually reduced the human population down to as little as 3,000 people, or about 1,500 breeding couples. Think about that. Think about where you live. If you live anywhere in the greater San Jose area, 3,000 people probably occupy a mile or two away from you. If you go to San Jose State, that is a tenth of the population at San Jose State. Or if you're at De Anza College, that is about a little bit less than a fifth. All of that to say that our entire human population was dwindled down to this really tiny number of people. And that's actually believed to have caused a genetic bottleneck. And yes, what this means is, genetically speaking, those 1,500 breeding couples are our great ancestors. For all intents and purposes, we came that close to being wiped off the face of the earth. That's pretty scary. And I should mention, Yellowstone and Toba aren't the only supervolcanoes out there. There are other supervolcanoes, including in the United States, that could trigger similar eruptions. Now let's talk about ice ages really quickly. So we are currently in the most recent ice age, the Pleistocene epoch. That being said, there's a big question that people ask: is what we're seeing now, this warming that we're experiencing, an emergence from the Pleistocene epoch? The answer to that is no. And here's why. The transition time from a warmer period to a colder period, at least in terms of talking about these major glacial periods and then these major warm periods, takes millions of years. The transition from the previous warm period, death of the dinosaurs, to where we are now took about 50 million years. So a cooling trend began about 55 million years ago, and it bottomed out about 2.5 million years ago. So that process, that transition time, was very long. I'm talking incredibly long. Now, the current ice age that we're in has not been continuous. There have actually been almost kind of like an ebb and flow period of advancing glaciers, then retreating glaciers, then advancing glaciers, then retreating glaciers. The most recent glacial advance we had was a period that occurred about 22,000 years ago. During that time, glaciers covered all of Canada, covered the United Kingdom, most of interior Europe, all of Russia was gone. Nobody was living, well, actually, some people were actually living in Alaska. Something else very interesting was happening in Alaska. And during that time, polar regions were anywhere between 15 to 20 degrees colder than they are today. Tropical regions were about 5 to 10 degrees colder than they are today, 5 to 10 degrees Fahrenheit colder than they are today. So it definitely was noticeably cooler worldwide. Well, because of this, and because of the fact that there was now so much more ice, that water had to come from somewhere. A lot of it came from the ocean. And so sea levels were on average about 400 feet lower than they are today. This actually exposed a huge chunk of seafloor between Alaska and Siberia. what is referred to as the Bering Land Bridge. It is believed that this is how humans were able to migrate from Asia to North America. So that is how people got onto the North American continent. Then about 14,000 years ago, we had a nice little warm spell. Then about 12,700 years ago, there was an abnormal period of sudden drastic cooling in the United States and Europe, known as the Younger Dryas. And there's actually a very, very possible and very frightening explanation for why the Younger Dryas may have happened and why it might be something we need to be worried about today. So that being said, here is just some evidence for the past 400,000 years of this ebb and flow that we've seen of glacier periods. There's definitely been a very cyclic nature between air temperature down here, where temperatures declined, then shot up, then declined again, then shot up, then declined again, then shot up. And so if you know these several different peaks, and please note there are multiple peaks, not just one big peak, there are multiple peaks. There are multiple peaks here. And this is based on Vostok ice core data. So the stuff that we talked about earlier in this module. And then up here, this is actually carbon dioxide concentrations. Carbon dioxide concentrations were up around 280 parts per million, then dropped down to about 180 parts per million, back up to close to 300, back down to about 180, back up to close to 300, in this case actually 280, back down and then up again, down and then up again. Once again, there are numerous peaks here. One of the things you're actually going to do for this week's module activities, you're actually going to pick apart this a little bit more. And I do want to really warn you, hopefully you will have watched this video before you actually attempt this assignment. There is more than one peak for each of these two things. There are multiple peaks and multiple bottoms. And so I want you to be able to actually identify each of them. That being said, this shows how climate has changed over roughly the past 400,000 years. Here's the frightening thing, though. First off, if you notice, the shape of these two graphs is extremely similar to one another. So there's clearly some kind of relationship between air temperature and carbon dioxide concentration. Now, I know it's very possible for some troll to watch this video. If you're there, hi troll, to watch this video and say, well, you know, it's very possible that the chicken came before the egg, or the egg came before the chicken. I will actually very clearly state that correlation does not prove causation, but there is a very strong correlation between these two. So there's something happening between these two, and based on the findings of Eunice Foote, based on observations from Guy Stewart Callender, there is a lot of information. There's a lot of evidence suggesting a relationship between these two things. And yeah, the question is kind of, well, is there actually some kind of well-known relationship between carbon dioxide and air temperature? I'd say yes, there is. So before you write the paragraph, probably the same one that you've written on other videos, just want you to know about that. The other thing that I want you to know is, and that's more just for the trolls out there who, you know, like to go to people's videos. And the other thing I'd like you to take a look at is, based on this temperature record and this carbon dioxide record, look at the range of carbon dioxide concentrations shown on this record. The range here is between 160 parts per million and 300 parts per million. Well, if you remember from Module 1, we are now somewhere around 415 parts per million. If I actually took this scale and were to draw a dot representing current carbon dioxide concentrations, it'd be right about there. And so this line, sorry for my terrible wiggly pen there, but this line basically shows that in just the recent times, carbon dioxide concentrations have skyrocketed. Now, once again, I can't say for sure that correlation proves causation, but if I were to postulate just simply based on this, here's what temperature would probably begin to do. I'll just write here, future temperature. So again, for this module activity, you're going to pick apart this graph a little bit more. The big thing I just want you to know, just please keep in mind, there's more than one peak for each of these, and there's more than one bottom for each of these. Just a little bit about our last big ice age. This was 18,000 years ago. As I mentioned, most of Canada was covered with ice. Much of the United States and the northern part of the United States was covered with ice. All of England was covered with ice. Much of interior Western and Central Europe was covered in ice. Sweden, Norway, Denmark, Scandinavia, all these areas up here, all covered with ice. Sorry, IKEA. Parts of Spain, the Alps up in France and Italy, parts of interior Italy covered in ice. So it was definitely a much colder place. And Iceland, in this case, was literally Iceland. So this was 18,000 years ago. And this is just showing a little bit about what was happening during that time. So here was the Pleistocene epoch. And this was that last glacial period. We saw a nice little bump in temperatures around 13,000 years ago. Then a sudden cooling. This cooling was mostly over North America and Europe. And then eventually temperatures recovered, and we kind of entered this nice little warm period. And then here's where we are now. If you take a look, we're starting to see a spike again. We're starting to see a spike again. All right. What may have actually caused the Younger Dryas? And why might it be a warning for our future? We're going to talk about that next.